Okay, in this lecture we're going to go over how to hydrate a double bond. And if you look at the word hydrate or hydration, it means you see the word a prefix meaning water, hydra. And so what are we actually doing in hydration of a double bond is we're adding water across the double bond. And what we're going to find is to add water to the double bond, there are 3 different ways. First of all, we can use water with acid. When we use water with acid, it can cause unintended reactions. And so it only works for the simplest molecules. If you use molecules that have other functional groups on it, oftentimes the acid will attack the other functional groups. And sometimes even for simple molecules, it can start causing polymerization. So it's not a very elegant way. It's kind of like using a sledgehammer to add water across a double bond, but it will work. It's just not great. There are 2 other gentle ways that are very selective, and these are the ones that we use more often in the laboratory. One of them does use mercury, which is kind of toxic, but we still do it and we just use it carefully. And we call that way oxymercuration. And then there's another way called hydroboration, which uses borane right here. Now, borane is written as boron with 3 hydrogens sometimes, and sometimes it's written as diborane. They mean the same thing. Borane doesn't exist alone by itself. When you have borane, it actually dimerizes and makes diborane here. So we write it both ways because we know that borane exists as diborane. Okay, let's go and look at these ways of adding water to a double bond and see how it occurs and what are some of the things that control how the water adds. Here is an example of a very simple compound to which we are going to add water. So here's the double bond that we're going to add water to, and here's water. The catalyst that we're using here is phosphoric acid, but it could have been sulfuric acid. Notice the high temperature at which you're running this reaction. This actually is a gas, so to run this reaction you would have to have an enclosed and pressurized container, which we call bombs. So you could either have sulfuric acid or you can have phosphoric acid as a catalyst here. What actually happens, if you look at the net effect, you can see on one carbon you get an alcohol group, OH, and on the other carbon, the other hydrogen in water becomes attached. It's not really showing you the attachment here because one of these hydrogens is purple over here. So notice a hydrogen gets added here and an alcohol group gets added. Oxymercuration is a set of reaction conditions that add water across a double bond that give much the same results as acid catalyzed hydration, except you get much higher yields. You do not have side reactions occurring, and it's very selective, very gentle. The mechanism we'll see is similar to the intermediate in the mechanism is similar to what we see with the halohydrins. And we say that the addition is Markovnikov addition because the hydroxyl group ends up on the more substituted carbon. Notice this is the more substituted carbon, and that's where the hydroxyl group ends up. And what we see happens is that mercury basically oxidizes a carbon in the double bond, and then the sodium borohydride actually reduces off the mercury and replaces it with a hydrogen. So let's go through this little mechanism here. Here is a unsymmetrical double bond. And the first reagent that we react with the alkene is mercuric acetate. That mercuric acetate adds by in very much the same way mechanistically that a bromine will add to make a bromonium ion. So these electrons reach out and grab the mercury, and then a mercury has electrons that reach down and form a bond here, and at the same time an acetate leaves, giving the mercury a positive charge. Once this mercurium ion forms, then water is going to do a backside attack, just like in the halohydrin formation. Where does it attack? It's going to attack at the more substituted carbon, because just like the bromonium ion, this little mercurium ion will open up slightly and put lots of positive charge here before the water will attack. So the water attacks to this side where it's more substituted, and then water adds to this double bond. It really is a protonated alcohol. The protonated alcohol gets deprotonated and the ring opens up. You're not going to be expected to draw this mechanism, so you don't have to worry about trying to remember what I'm telling you here. But I do expect that you know that this intermediate is formed and this intermediate is formed. Then once this intermediate is formed from the addition of mercuric acetate to the alkene, then what happens is sodium borohydride is used to reduce the mercury off of the carbon, and you end up getting water added across the double bond in Markovnikov addition, and it has really high yields. Now you have to be really careful handling mercury because it's toxic, but if you have a good lab technique, you don't really have to worry about it, and you get excellent yields from this. There's another way to hydrate a double bond so that you get anti-Markovnikov addition, and this is called hydroboration. If I look at this double bond here, you can see it's asymmetrical. This has two alkyl groups on it, and this only has one. We can take borane, although it's sometimes written as diborane, B2H6. We can take that, and when we mix it with an alkene, what happens is it sits down on the double bond. Now, what we've been showing you so far, when two things are added to a double bond, we're showing with the bromonium ion and with the mercurium ion that you have anti-addition. But with the borane, what actually happens is synaddition, where you have the hydrogen sit down over here and the boron sit down over here at the same time, and as they sit down, the double bond here breaks and the bond up here breaks, so they add to the same side of the double bond. Okay, this is intermediate. In fact, there's actually many more intermediates, because this will then do addition to another double bond and another double bond, and so you get the more complex intermediate. This really is the simplest way to look at the intermediate, but you'll see other drawings for this. Once this intermediate is formed, then what happens is you oxidize the boron off the carbon, leaving an alcohol group there. This is really kind of interesting because with the mercuric acetate, you do an oxidation with mercuric acetate and then a reduction with the sodium borohydride. With hydroboration, you do a reduction with the borane, and then you do an oxidation with hydrogen peroxide. And both of them give you the addition of water across the double bond. It's just the mercuric acetate, sodium borohydride reagents give you Markovnikov addition, and the borane hydrogen peroxide reagents give you anti-Markovnikov addition. So here's an example. Here is an alkene, and here is borane. And here we're showing it adding to 3 different alkenes. Remember, I showed you the simplest way is to look at it as hydrogen added here and what would be boron with 2 hydrogens attached, but it keeps on reacting, and it actually will make, borane will add to 3 alkenes. Then what happens is use hydrogen peroxide and it oxidizes the boron off and leaves you with an alcohol in each place of where the boron was attached. Okay, this is showing you, this is syn, same side. Notice that when the borane attaches, it's same side attachment. When the hydrogen peroxide is used to oxidize it off, the reaction actually occurs on the boron, so it leaves it as syn addition. Okay, this is going through the mechanism of hydroboration to show you how the syn addition occurs. Notice that the borane comes up right on top of a double bond, and as it does, the double bond breaks, these 2 bonds form, and the boron-hydrogen bond breaks. Notice the hydrogen is going to the the more substituted carbon, and the boron goes to the less substituted carbon. This is important. The reason that it happens is that this is a bulkier side to the borane than just the hydrogen, and this is the bulkier side to the alkene than just the hydrogen over here. So for steric hindrance reasons, the boron gets shuttled to the less substituted carbon, the hydrogen to the more substituted carbon. But what happens also is that boron is less electronegative than hydrogen. So the hydrogen has a del negative charge and the boron has a del positive charge. As a result, when these go in, this can hold del positive better, this can hold del negative better. Del positive starts developing on this carbon, and the hydrogen is attracted to del positive on this carbon and boron to this one. So there's actually charge development also directs the hydrogen to the more substituted carbon. What is the key thing is that you know it's syn addition of the boron and hydrogen, and that the hydrogen ends up on the more substituted carbon, so it's anti-Markovnikov addition for the alcohol. So here are 2 examples. Here is cyclopentene. We treat it with borane and hydrogen peroxide and hydroxide, and you get syn addition. Notice there's a hydrogen down here that's not written, and then here's the alcohol. So it's syn addition, and notice that the alcohol is on the less substituted carbon. Whereas when we do the same reaction with mercuric acetate followed by sodium borohydride, what do we see? We have the hydroxyl group go to the more substituted carbon. Here's another example. Here is an asymmetrical alkene. If you treat it with borane and followed by hydrogen peroxide and hydroxide, what do you get? You get the alcohol on the less substituted carbon. Whereas with mercuric acetate, followed by sodium borohydride in base, what do you get? You get the alcohol on the more substituted carbon. Okay, so here's a you try it for you. Go ahead and try these 2 reactions. Pause the lecture, restart it after you've gotten an answer. Okay, treating methylene cyclohexane with borane followed by hydrogen peroxide and base, what do we get? We get anti-Markovnikov addition. Notice the alcohol group is on the less substituted carbon, and there is a hydrogen here that was added to the double bond that's not written. It's just understood that it's there. If I look at this reaction, I see that I have 1-methyl cyclohexene. If I treat it with deuterated borane, what will happen? I will get the boron adding to the less substituted carbon, and the deuterium, which is just like hydrogen, just one extra neutron, added to the more substituted carbon, and then oxidation with peroxide changes that to hydroxide. So we have anti-Mark addition for the hydroxyl group, and notice it's syn. The deuterium and the hydroxyl group are on the same side of the ring. What are the products of these reactions? Figure in an answer and then restart the lecture. The product of this reaction is that this is the more substituted carbon. So the mercury, you'll make the mercurium ion here. Excuse me. Yes, the mercurium ion right here. And then it will ring open to put a little bit more positive charge here. So water attacks there, putting the hydroxyl group on this carbon, and then after the mercury will end up on this carbon, and the sodium borohydride will reduce the mercury down to the hydrogen here. For this compound, it's a symmetrical compound, so it doesn't really matter which carbon you're going to put the oxygen on. However, you have to note that it's deuterium that's being put on the carbon opposite it in the double bond. See the deuterium here in the sodium borohydride? This is where the mercury was, and so that's where the deuterium ends up.